Venus. Our, at times, closest planetary neighbour and our sister world. Similar in size to the Earth, but about 40 million kilometers closer in orbit to the Sun, the second planet of our solar system has long been the source of stories, myths, and legends. In more recent times, however, we have gone beyond seeing just that bright circle close to the Sun at the start and end of the day. Beginning at the height of the Cold War, numerous robotic missions have been sent to Venus to observe, orbit, and in some cases, even land. And using technology that sees in not only the visible light, but also in the infrared, ultraviolet, and radio spectra, what we have found is a world that is different to Earth in almost every way imaginable. I'm Alex McColgan, and you're watching Astrum.
Join us today on this Supercut as we take a journey to the star of the morning and the evening,
using technology both old and new to uncover the secrets of Venus and descending through its thick atmosphere to arrive at the surface of our closest companion.
Venus is the second planet from the Sun, and it's our closest neighbour. Its average orbital radius around the Sun is 0.72 astronomical units, or roughly 108 million kilometers. It doesn't vary much at all from this mean orbital radius, as it's the planet with the least eccentric orbit, orbiting in a nearly perfect circle. At Venus's closest approach to us, it is the closest of any other planet, being only 41 million kilometers away. Interestingly though, this is not when it's brightest in our sky, as when it's closest to us, we only see the night side, as it's between us and the Sun. It is still visible though, as the sunlight refracts through the atmosphere. It's actually brightest when it's a thinner crescent shape in the sky, and when this happens, it is the brightest object we see at night after the moon. As such, Venus is commonly misreported as an unidentified flying object. US President Jimmy Carter reported having seen a UFO in 1969, which later analysis suggested was probably Venus. Countless other people have mistaken Venus for something more exotic due to its startling brightness. I recently had the pleasure of looking at Venus through a telescope, and remarkably, the crescent shape of it was very visible. With Venus orbiting between us and the Sun, it may make you wonder if Venus ever eclipses the Sun from our viewpoint on Earth. And the answer is yes, but surprisingly very rarely. Transits happen in pairs, the pairs being 8 years apart, but every pair only happens once every 100 years or so. The last transit we had was in 2012, but if you didn't see that, I'm afraid the next one won't be until 2117. The reason for this rarity is because the orbiting plane of Venus is not exactly the same as Earth's. Also, Venus only catches up with Earth every 584 or so days. These two things combined ensure that, although a spectacular and predictable sight, it also means we'll probably only ever have the chance to see it once or twice in our lifetimes. All the planets orbit anti-clockwise around the Sun, and with this, Venus is no different. But unlike all the other planets, it rotates clockwise, or in other words, in a retrograde rotation. Not only that, but it has an extremely slow rotation, rotating once every 243 Earth days, slower than any other planet. This makes a sidereal day longer than a Venusian year, a Venusian year lasting 224 Earth days. A sidereal day, if you remember from my Mercury episode, which you can check out here if you missed it, is one rotation of the planet. Because of this retrograde rotation, however, a solar day, which is sunrise to sunrise, is considerably shorter, at 117 Earth days. This means you'd experience just less than 2 days on Venus in 1 year. To give you some perspective as to how slowly it rotates, at the equator, the planet is only rotating at 6.5 kilometers an hour. This slow rotation makes it the second most spherical object in the solar system after the Sun. It is unclear why Venus rotates backwards compared to the rest of the planets, but it could be due to a big impact with another object billions of years ago, or tidal locking with the Sun, or tidal effects on the Venusian atmosphere. So far, these are all things we can learn through long-range observations, taken from right here on Earth. But for many years, that was all we had to go on. Much like a coy and flirtatious lover, the planet Venus cloaks itself in a literal air of mystery, a thick and shrouding fog that hides its secrets. And convincing Venus to relinquish those mysteries would prove to be no easy task, as the first scientists who tried to woo her found to their dismay. I do find it ironic that for a planet named after the goddess of love, Venus is one of the most treacherous and hostile worlds imaginable. That either feels very wrong or very right. Let's take a look at those early efforts to explore Venus's hidden surface. What did they learn? And what can we find on the true face of Venus?
As the second brightest object in the night sky, and also the closest, barring the moon in terms of distance, sometimes, Venus has always attracted attention from those who would gaze up at the heavens. But even today, interplanetary travel is hard, and at the height of the Cold War, it was even harder. Of the 15 missions launched to explore Venus between 1961 and 1967, only 3 were classified as successes in terms of fulfilling their specific objectives: Mariners 2 and 5 from NASA, and Venera 4 from the Soviet MPO Lavochkin. Successful atmospheric entries with Venera 4, 5 and 6 soon followed, and in late 1970, the USSR finally passed a massive milestone with Venera 7, the first space probe to land on the surface of another world and last long enough to send back information about it. Come with me as we follow Venera down into those treacherous, obscuring clouds to see what lies beneath. Still drifting through space, Venera turns towards Venus. As it begins its descent onto the planet, Venus's upper atmosphere lies before it, extending from the fringes of space at around 250 kilometers above the surface and down to around 60 kilometers above it. Here, it sees nothing but a thin haze. 99% of Venus's atmosphere by mass lies below this point. This makes Venera's descent through this layer easy enough, in very much the same way as our own atmosphere would be at similar altitudes. But Venus's upper atmosphere's chemical composition could not be more different, a sign of things to come as we and Venera descend further. Instead of a majority of nitrogen and oxygen, as on Earth, we begin to pick up traces of carbon dioxide. It's not enough to cause significant effects on the temperature at this altitude, but it's significant as a marker of what lies beneath. Other than the difference in chemistry, however, at this altitude, the atmosphere behaves roughly the same as that of our home planet at similar altitudes, with vast temperature differences between day and night, highs of -37 degrees Celsius to lows of -143 degrees Celsius. For Venera, this is the easy part. An interesting sideshow to the noticeable presence of carbon dioxide is the presence of some oxygen atoms, which emit infrared radiation that can be seen by telescopes and spacecraft. In this picture taken by the Venus Express orbiter in the infrared wavelength, the blue is the air glow caused by the oxygen high in the Venusian atmosphere. As Venera moves downward through the layers, it comes to the main visible cloud deck of Venus at around 60 kilometers from the surface. The thick, dull yellow that we associate with pictures in visible light is almost entirely because of this cloud deck, terminating approximately 40 kilometers from the ground. In this part of the atmosphere, ultraviolet radiation from the sun breaks up carbon dioxide into carbon monoxide and single oxygen atoms. These atoms then easily react with sulfur dioxide and water vapor, 2 other trace compounds in the Venusian atmosphere, to produce the clouds of sulfuric acid that we see. Sulfuric acid, just as a side note,
is highly corrosive, and the resulting acid rain just adds to the hellish nature of Venus, although it does evaporate before it hits the surface. But that is still to come. For now, this is the calm before the storm, the relatively temperate region before the real hell that Venera must soon enter. As Venera enters that chaotic churn of violent acidic cloud, it likely would appreciate it if it could take a little of that earlier tranquility with it. Sometimes I feel like that too when I've got a chaotic day ahead. Perhaps Venera could listen to podcasts or its favourite music when it's making the dive, or with the help of Raycon, the sponsor of today's video. Raycon's essential open earbuds are ideal for keeping aware of what's going on around you while not sacrificing audio quality on your podcast or music. They are lightweight, helpful for humans or NASA spacecraft, and their secure fit means that they won't fall out even after hours of wear, which, by the way, they can manage thanks to their 8 hours of battery life. I actually find this product really comfortable, and they manage to deliver similar levels of audio quality to competitor brands while coming in at about half the price. Why not give them a try yourself? Raycon's essential open earbuds come with a 30-day money-back guarantee, so there's no risk. Just click the link buyraycon.com/Astrum Open and you'll get 20% off site-wide. It's a great way to support the channel. Now, back to Venera. As you can immediately tell, the surface of Venus cannot be seen through the planet's thick cloud cover, so Venera will have to go in blind. That same cover reflects around 3/4 of the sunlight that hits Venus, sometimes letting as little as 10% of the sunlight through, as the ice crystals formed from the sulfuric acid that floats in the atmosphere are extremely reflective. This reflectivity goes a long way towards explaining how bright Venus looks, both to satellites going by and to observers on Earth. Remember, it's the second brightest object in the night sky. These clouds are also capable of producing lightning, much like on Earth, although it's not as common. When we look at those mustard yellow clouds in the visible spectrum, they appear thick and obscuring, revealing little of what lies beneath. However, we have an advantage that Venera did not possess: infrared sensor technology. In the infrared spectrum, things look a lot different. This image taken by the JAXA spacecraft Akatsuki throws things into much sharper relief, showing clear light and dark spots and bands wrapping around Venus's atmosphere. And here is where we see the thick carbon dioxide composition of the atmosphere very clearly indeed. Carbon dioxide is an effective greenhouse gas, trapping the heat that derives from the sun, resulting in an incredibly high surface and atmospheric temperature. Under the scope of infrared observation, this becomes very apparent as the entire surface glows under the heat generated by the thick layer of carbon dioxide. The dark patches and stripes are the previously mentioned clouds of sulfuric acid, and we can see them high above the much brighter, thick and hot carbon dioxide layer near the surface. Can you imagine what Venera would experience as it travels through this hell? Sulfuric acid assaults its outer casing. Winds blow at 100 meters per second, 60 times the rotation speed of the planet, fast enough to circumnavigate the planet in just 4 days, which makes the planet look like it's rotating a lot faster than it actually is. The temperature, which at an altitude of 50 to 55 kilometers is anywhere between 25 to 75 degrees Celsius, sharply rises, reaching blistering levels. Surface air pressure on Venus is 75 to 100 times what you'd find on Earth. Comparably, it's like having an entire car sitting on your thumbnail. As Venera descends further, however, even weirder conditions can be found. Once Venera passes through the bottom of the sulfuric acid cloud deck, it arrives in clean air once again. But things here are strange. The pressure here is now so great, it's starting to have an effect on the carbon dioxide in the atmosphere. The density of carbon dioxide at this level is so high that it no longer acts as a gas, but more as a kind of supercritical fluid.
a state of matter somewhere between liquid and gas, where a substance takes on some of the characteristics of both. The wind has slowed down here after the baffling fast speeds of the upper clouds. The atmosphere below is so thick that winds blow at little more than 5 kilometers per hour. It would feel like wading through water with a slow but inexorable current, albeit in a river that is 464 degrees Celsius, hot enough to melt lead. For point of comparison, that makes it 34 degrees Celsius hotter than Mercury's peak temperature, even though Mercury is closer to the Sun, and Venus only gets 25% of the solar radiation that Mercury does. The difference is that Mercury doesn't have an atmosphere to retain the heat, whereas Venus certainly does. This means at night time, and even at the poles, the temperature remains fairly constant. While much of this surface might feel alien to us back on Earth, there's one similarity: the level of gravity. Venus's size and mass are very similar to our Earth, hence why it's often referred to as our sister or twin planet. Venus is one of the 4 inner terrestrial planets, and it is a rocky planet. Its diameter is slightly smaller than Earth's at 12,100 kilometers compared to Earth's 12,740 kilometers, and its density is 5.3 grams per centimeter cubed compared to our 5.5 grams per centimeter cubed. This means the gravity on Venus is only a tenth weaker than that on Earth, surface gravity being 8.9 meters per second squared. But what can modern technology tell us of Venus and its layers? To further illustrate the vast heat at this altitude level on Venus, let's look at a picture of the lower atmosphere of Venus taken in the near-infrared range, a wavelength of 2.3 micrometers by the Galileo satellite. The red, hot areas of the lower atmosphere are clearly visible, as are the darker patches caused by the clouds of sulfuric acid higher in the atmosphere. The lower reaches of the Venusian atmosphere are incredibly hot, and there are distinct layers of that atmosphere different in both temperature and composition. To further demonstrate the differences between the atmospheric layers of Venus, let's now have a look at the layers we've seen so far under ultraviolet light. While the images, again from the JAXA spacecraft, taken in the 283 and 365 nanometer wavelengths do not show much contrast in color and brightness as the infrared images, they do show more variance than ones viewed in visible light. The areas of darkness and blotchiness of the cloud layers indicate the ultraviolet light is being absorbed rather than reflected. But exactly what chemical or combination of chemicals causes this absorption is still a matter of debate among the astronomy community. Clearly, there are elements and compounds of the Venusian atmosphere that still evade our attempts to discover and categorize them. And on the subject of Venus's atmosphere defying explanation, here's a look at Venus's poles in the infrared. Notice anything strange about them? Present at both Venus's north and south poles are large polar vortexes, about the size of Europe, whipped up by those 100 meters per second winds. What's really weird though is that they have not just one central eye, but 2, and scientists are still not quite sure why. Venus's complex, highly variable polar vortexes are extremely hard to model, as they can change on timescales of less than 24 hours, making them quite the mystery. But once it was past the enigmatic atmosphere, what did Venera see down there? Let's conclude Venera's journey through the thick acidic clouds and arrive at the surface of our closest companion. Earlier, we saw the very first image ever sent from the surface of Venus. Due to the massive clouds of sulfuric acid obscuring any kind of view from space, the only images of Venus that show the surface in visible light are those that have been taken from a lander on the surface. And of those, we only have 6, taken from 4 of the Soviet Venera probes that landed, such as our Venera 7. The air is surprisingly clear. Scientists had wondered whether everything would be obscured by a thick haze, but this doesn't appear to be the case. Everything is a dull yellow, the colour of the acidic composition of the atmosphere, and while we might be surprised to find solid, rocky ground under the thick, crushing air of Venus, that ground is also utterly desolate. It hints at ancient lava flows now hardened into flat plains and eroded under Venus's intense atmosphere. Everything seems very dry, which is unsurprising given the baking heat. Perhaps a billion years into the future, when the sun has increased luminosity enough, we might see similar runaway greenhouse effects and results on Earth. But here we must leave Venera. The Venera series of probes, including the one whose journey we have been following, never lasted more than a couple of hours on Venus's surface due to the combination of heat and crushing pressure. Their images give us a brief but vital glimpse into conditions down there on the rocky ground.
But while fascinating, these insights into the surface conditions on Venus fell far short of what scientists wanted to know. After all, Venera's photographs only covered a tiny fraction of the planet's surface area. But if landing probes on the planet's surface was proving almost impossible, was there another way to peer through Venus's cloying clouds? It turned out there was.
It's not infrared or ultraviolet. Neither infrared nor ultraviolet imaging can break through the thick, cloudy atmosphere to see and map the surface with any kind of clarity. You need something different. Step forward, radar imaging.
In the 1970s, the Pioneer Venus orbiter, also known as Pioneer Venus 1 or Pioneer 12, provided some radar mapping data, but its resolution was low and its images incomplete. Imagine trying to map the Earth, but Google Maps didn't let you zoom in further than 75 kilometers. New York City would just be 1 pixel, so pretty hard to make an accurate map. Additionally, Pioneer 12 didn't map the northern and southernmost parts of Venus. That's like a map of Earth with most of the Arctic and Antarctic circles missing.
The USSR began the process of using radar to map the surface of Venus with their later Venera models, 15 and 16, in 1983, producing images with a resolution of 1 to 2 kilometers on the ground. NASA decided they could do better. They wanted to see it all: landforms, tectonics, impact and chemical processes, erosion, and even get to know Venus's interior. So, they mounted an ambitious mission to capture the entire surface of the planet in ultra-high detail, along with a gravitational map that would give insights into what lies beneath. That mission was Magellan. Now, before I show you Magellan's photos, you need to understand 3 key engineering innovations that made Magellan's mission so groundbreaking. First, to penetrate Venus's dense atmosphere, Magellan improved on Pioneer's basic radar altimetry. Engineers used a 3.7 meter high-gain Voyager antenna and components from other past missions to create a synthetic aperture radar that collected multiple readings of each area from different orbital positions. These combined readings simulated observations from a much larger antenna, revealing unprecedented surface details. Second, Magellan followed a polar orbital path, scanning Venus in north-south strips during each of its 3-hour, 15-minute orbits. In total, it completed 6 243-day mapping cycles. Cycles 1 to 3 mapped the planet's surface, and cycles 4 to 6 captured gravitational field data. By the end of its first cycle on the 15th of May 1991, Magellan exceeded its 70% mapping goal, covering 83.7%. By the end of cycle 3, it had mapped 98% of Venus at 100 to 250 meter resolution. The probe ended up sending home more data than all of NASA's previous planetary missions combined, a total of 150 gigabytes. By today's standard, it admittedly isn't that impressive. Your phone probably has more storage capacity.
but for the early 90s, it was quite something. Finally, after its third mapping cycle in September 1992, Magellan transmitted a continuous radio signal to NASA's Deep Space Network. Based on how the probe's acceleration changed as it orbited the planet, this would produce a change to the radio signal via the Doppler effect, allowing scientists to decipher Venus's gravity field. This revealed information about the planet's interior structure and density distribution. The images I'm about to show you are 10 times sharper than any previous radar images taken from Earth or orbiting spacecraft at the time, and 250 times sharper than Pioneer 12's data. For the first time, we actually got to see what was lurking under those thick, noxious clouds. Let's take a look. Where previous missions had only shown vague outlines, Magellan revealed a world in exquisite detail, revealing for the first time the surface characteristics of our next door neighbor. This mosaic took a decade to put together, with the bulk of the radar data coming from Magellan's readings. When you approach Venus, you immediately notice the lack of craters. Compared with the Moon or Mars, it's pretty untouched, with Magellan only identifying 940 impact craters across the entire planet. Many small impact craters are missing because their meteors burn up in Venus's atmosphere, and the other craters we did find didn't look as expected. Take these three craters for example: Howe, Danilova, and Aglaonis. On impact, debris from the surface is ejected and forms the pale yellow blanket-like formations around each crater. Crater ejecta leave behind distinctive marks and shapes that help scientists determine the angle and energy of impact and how long ago it happened, the composition of surface and subsurface materials, and much more. What's interesting about these crater ejecta is they all show sinuous flows in a flower-shaped pattern, not unlike lava flows. They are made of molten rock and remain this way for way longer than expected due to Venus's high surface temperatures. The Adivar crater is another great example of Venus's unique ejecta patterns. On airless worlds like the Moon, ejected material from the impact follows an arced, ballistic path. But on Venus, the ejected debris interacts with the planet's dense atmosphere, creating powerful winds that sweep the material outward in ground-hugging flows. This creates unusual streaks, like the horseshoe-shaped one we see here, which are only found on Venus. Finally, the 90-kilometer wide Adams crater has a 600-kilometer outflow tail, likely made of impact melt or magma, which can remain in its liquid form for much longer due to the high temperature and pressure on Venus. The scarcity of these craters suggests Venus's surface is actually quite young. Indeed, gravity data collected by Magellan supports the hypothesis that Venus underwent a global resurfacing event approximately 300 to 500 million years ago. So, what could have caused such a dramatic event? Volcanoes? Lots and lots of volcanoes. We knew Venus had volcanic features before Magellan, but we had no idea that a staggering 85% of the planet is covered in volcanic flows. Like these pancake domes, 65 kilometers wide with broad, flat tops less than 1 kilometer tall. They likely formed from highly viscous lava, which later cooled and withdrew, leading to the cracks and pits you can see in the image. Or these sprawling lava flows, stretching for hundreds of kilometers over the fractured plains beneath two large shield volcanoes, Sapus Mons and Mart Mons. By studying the varying shapes and patterns of these volcanic plains, scientists can identify different volcanic formation processes, from localized shield volcano eruptions to massive regional lava flooding events. Speaking of Mart Mons, let's take a closer look. Towering at a dizzying 8,000 meters tall, it's almost as large as Mount Everest. It's also a shield volcano, characterized by its broad, gently sloping sides. They are typically formed by fluid lava flows, like the Mauna Loa in Hawaii. Shield volcanoes are not the only kind of volcano you'll see on Venus. Small volcanic domes like these are also very common features on the planet's surface. Unlike shield volcanoes, volcanic domes are formed by small, bulbous masses of lava too thick to flow very far. As it slowly exits the vent, the lava piles up and cools on the sides. This cluster of volcanoes sits between rough lava flows in the east and smooth lava flows in the west, indicating two different types of lava overlapping, though the exact process remains unknown. The abundance of lava flows and volcanic features on Venus confirmed that volcanism played a dominant role in shaping Venus's surface, and gave rise to the theory that the planet might still be volcanically active to this day. In 2024, researchers who were revisiting Magellan's archival data found that 2 volcanoes actually erupted during the probe's watch in the early 1990s. This supported a historic finding from the previous year that Mart Mons had also erupted in 1991. So, what's going on beneath the surface? What is Venus's mantle like? A hint to those answers lies in the surface coronae, like this 500-kilometer wide Yavin corona. When hot, upwelling magma from the depths of a planet's mantle reaches the surface, or the lithosphere, it leaves its mark. On Earth, our tectonic plates shift over this magma hotspot, creating volcanic chains like Hawaii or flood basalts. But Venus only has one single tectonic plate, so mantle plume activity pushes the surface upward before collapsing as the magma cools. The result? These coronae. Despite being hundreds of millions of years old, many coronae appear well preserved. There are around 500 of them, widely distributed across the planet in patterns inconsistent with plate boundaries, and their characteristics suggest a lithosphere that is too thick or strong to break into mobile plates like Earth's. All this evidence suggests a unique style of lithospheric deformation where the crust stays largely in place, but is pushed, pulled, and deformed by forces below. This stagnant lid planet model might also play a role in Venus's runaway greenhouse effect. On Earth, our tectonic plates carry out vital processes like burying oceanic carbon. When it rains, atmospheric carbon interacts with mountain rocks to create new minerals which slowly make their way to the oceans and eventually find themselves stored in seabed sediment. This sediment is then subducted when an oceanic plate sinks the seabed back into Earth's magma layer, a process that regulates Earth's temperatures and the concentration of carbon dioxide in our atmosphere. Since Venus's crust is stagnant and devoid of tectonic activity, this regulatory process can't take place. Instead, heat builds up beneath the surface and greenhouse gases are not effectively removed from the atmosphere. The hotter the interior becomes, the more unstable the system, until the whole lithosphere overturns in a global resurfacing event, and the cycle begins again. We aren't exactly sure when the last resurfacing event occurred on Venus, but NASA's technical report following Magellan suggests it happened about 300 million years ago. Another curious symptom of Venus's unique tectonics and mantle activity are the tesserae that we can see in the highland regions of the planet. They are distinct geological features characterized by highly deformed terrain with a tile-like appearance. They cover about 8% of Venus's surface and are primarily found in the highland regions. As some of the oldest visible surface features on Venus, they date back about 750 million years. The USSR's Venera 15 and 16 missions first identified these formations in the 80s, but Magellan brought them to life in spectacular detail, like this photo of Alpha Regio, one of the most prominent tesserae on Venus. Scientists still aren't sure exactly how tesserae form, but the two leading theories indicate they are likely made of volcanic rocks, or they are part of Venus's continental crust, deformed through compression or expansion. If so, they'd be gateways into Venus's geological past, and possibly even show us what the climate was like billions of years ago. Fascinatingly, Magellan actually managed to capture the first evidence of active tectonics occurring on another planet in the solar system, in Venus's Aphrodite Terra, a continental area roughly the size of Africa. The image on the left was taken in late November of 1990 during Magellan's first trip around Venus. The image on the right was taken 8 months later, as the spacecraft flew over the region for the second time. See the bright, flow-like area that appeared? It's likely the result of a landslide, which was possibly triggered by a Venus quake. On the 13th of October 1994, after completing one of the most successful deep space missions ever, the probe made its final descent into the atmosphere of the planet it had studied so devoutly over the last 4 years. As it plunged towards the surface, it continued to transmit data about Venus's upper atmosphere until it was consumed by the intense heat and pressure. So, with all we now know about our nearest planetary neighbour, what remains to be discovered from Venus in the future? The answer is a lot. In recent times, by far the biggest news regarding Venus has been the discovery, or perhaps not, of the gas phosphine high in the Venusian atmosphere. In 2020, measurements from the James Clerk Maxwell Telescope indicated the presence of trace amounts of the gas. Phosphine is produced through a variety of different processes, but one of those, and the one that got everyone excited, is through microbes in low oxygen environment. Life in one of the most unlikely, hellish places imaginable? What an outcome that would be. However, subsequent studies found no such phosphine again, and by 2022, the idea of it being present in the Venusian atmosphere had been dismissed by NASA. It would have appeared that the findings of the initial study were in error. But then, Professor Jane Greaves of the University of Cardiff went on record at a prestigious meeting in 2023 that the JCMT had found phosphine once again, this time deeper within the atmosphere of Venus. Hopefully, future missions will give us a definitive answer to this truly tantalizing question. Many other questions await answers too. Why, for instance, did two planets, Venus and Earth, so similar in size, evolve so differently? Was there in fact liquid water on the surface once upon a time? What is a more accurate picture of the chemical composition of both the Venusian atmosphere and the surface that might help answer these conundrums? After decades of being relatively overlooked in favor of Earth orbit assignments and outer planetary probes, Venus has suddenly garnered interest again. Several missions are scheduled to be launched for Venus within the next 10 years. NASA's upcoming Veritas and Da Vinci missions will, hopefully, set out to answer questions like, was there ever water on Venus? If there was, would Venus have been habitable? How has the planet evolved through time? Is Venus still volcanically active today? And many more questions. Currently scheduled to launch in 2028 to 2030, if they proceed, they will revolutionize our understanding of Venus once again. Da Vinci Plus will study Venus's clouds during 2 gravity assist flybys, and also send a descent probe deep into Venus's atmosphere to get a better understanding of its gases, chemistry, and water history. Even though it isn't expected to survive the landing, the probe will collect valuable data and images on its hour-long descent to the planet's scorched surface. Meanwhile, the Veritas spacecraft will be a Venus orbiter, similar to Maven currently orbiting Mars, Over the 3 Earth years it spends circling our neighbour, its job will be to search for evidence of ongoing volcanism and tectonic activity by measuring heat coming from the surface and analysing the composition of Venus's tesserae. These findings will, hopefully, help us understand just how different, or similar, Venus and Earth are. Regrettably, I can't discuss these missions without that caveat, if they proceed, as Veritas and Da Vinci are both missions that will be cancelled if NASA's proposed budget cuts go through. MAVEN is already around Mars, and yet it too could be turned off to save money. You can learn about those budget cuts here, along with my opinion on it, but for now let's just cross our fingers that these illuminating missions are allowed to go ahead as planned. But even if they do not, the other nations of the world are stepping up. ESA, Russia, China, India, and even one private American venture, the Venus Life Finder, are all planning missions with ambitions that lie Venusward.
With any luck, one, more, or all of them will lead us on a voyage of great discovery about our beloved star of the morning and evening, divulging a wealth of information and answering some of our burning questions about Venus. So there we have it. Looking at Venus through a variety of differing wavelengths has given us far more knowledge than visible light alone could give. We have been able to discern volcano and crater formations through kilometers of opaque clouds, determine some of the chemical composition of both atmosphere and surface, and use infrared imaging to make the invisible visible to us. All of these have granted us precious hints as to why the conditions on it are so extreme, and just maybe that there is the possibility, however slim, of simple microbial life on our closest neighbour.
What would you like to learn about Venus? What is your favourite aspect of it that stands out the most to you? Let me know in the comments below. But for now, I'm Alex McColgan, and this has been Astrum. I'll see you again next time. Thanks for watching. I really want to give a huge thank you to our astronauts on Patreon. It's really becoming a thriving community, and I've loved reading all your messages and comments over there. If you'd like to join in, then you can visit the link in the description to become an astronaut and bring the channel more stability than the algorithm. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.